Hello, my name is Mohamad Orabi. I am a graduate student at UC Irvine, and today I'm going to present my work on a machine learning multipath mitigation approach for opportunistic navigation with 5G signals. So, as we all know, ever since the development of GNSS, they have been the leading providers for positioning solutions. But these systems have some well known vulnerabilities, and the need to address them is becoming more and more critical, especially as we move towards a more modern world, where instead of pulling up your phone to order an Uber, you can order UAM, and where packages you order online could be delivered to you within minutes via UAVs. Now, although these things might seem futuristic, Uber already has plans to launch Uber Air in 2023, and some of you might have even heard of Amazon's Prime Air as well. Now, generally speaking, these autonomous vehicles depend on GNSS along with other sensors such as IMU, LiDAR, and so on and so forth. But is that really enough to prevent any accidents? And what kind of performance could we expect if the GNSS signals were compromised, either due to a challenging environment, interference, or even jamming? Well, we have already asked and answered a similar question here at our lab. In September of 2019, we were invited by the Air Force to conduct experiments during live GPS jamming. And as you can see here, the GPS IMU solution in red drifts to a final error of about 800 meters. And this is using a $10,000 GPS IMU system. If we used our phones instead, this is what Google Maps was showing. You can see the blue uncertainty halo grow up to 6 kilometers. So, does this mean we are never going to get to the point we envisioned? Absolutely not. We can turn to opportunistic navigation and exploit the ambient signals all around us. Now, if we look at the blue curve, we can see that it does much better in GPS denied environments. This curve represents the navigation solution produced using only one signal of opportunity, or SOP, from a single LTE tower. But today, we will focus on the next generation of cellular signals, 5G. So, what kind of advantages does 5G provide over GNSS? Well, they have a higher received signal power since they are terrestrial signals, and they have a very wide operating band, making it more resilient to spoofing and jamming attacks. They also provide bandwidths of up to 400 megahertz that are very attractive for navigation purposes, and on top of all that, they utilize an existing infrastructure that is constantly being updated and improved. Now, all these opportunities triggered a renaissance of research in 5G based positioning solutions, where a lot of the approaches study the positioning capabilities of 5G signals and demonstrate impressive results but are limited to simulations. Some approaches have shown experimental demonstrations as well, achieving ranging errors with a standard deviation of 1.9 meters, and our previous work featured in Inside GNSS was the first to produce a navigation solution with 5G signals achieving an RMSE of 4.1 meters. And of course, with machine learning leading to breakthroughs in various fields, it has made its way to navigation, where neural networks have been used for multipath detection, aiding fingerprinting and time of arrival estimation methods, and even enabling a novel synthetic aperture approach for direction of arrival estimation with LTE signals. But life doesn't serve things on a silver platter, and there are a few challenges to overcome to be able to navigate with 5G signals. For starters, terrestrial signals have lower elevation angles, leading to more severe multipath. We also don't have a database of 5G towers specifying important information like position and carrier frequency. And since they weren't meant for navigation, their clocks are not as stable or as tightly synced as GNSS satellites. And we also need to design specialized receivers since we are after navigation observables and not data. In this presentation, however, we will be focusing on the first problem, proposing a machine learning approach to mitigate multipath. And this leads us to our contributions, which is mainly assessing different types of neural networks for the problem of multipath mitigation. Feed-forward neural networks achieved an RMC reduction of 40% during training and 30% during validation, while time delay neural networks achieved a reduction of 56 and 60% on those sets. Both of these networks fall under supervised learning, but if you stick around till the end of the presentation, you will get to see another approach we are currently developing that wasn't mentioned in the paper. Finally, we present an experimental demonstration that show that the results can be generalized beyond simulations. Okay, so in order to properly formulate the problem, we need to take a closer look at how a receiver works and how multipath enters the system and corrupts the time of arrival estimates. First, the reference signals are generated, which are the primary and secondary synchronization signals specific to 5G in this case. Then, these signals are correlated with the received signal, and due to their favorable auto and cross correlation properties, the autocorrelation function, or ACF, shows a sync shaped peak, as you can see in this figure produced with experimental data. The ACF is then used by the delay locked loop, or DLL, to track the code phase, which it does using a discriminator and a loop filter. So obviously, the DLL plays an important role in the receiver, and indeed, it's an important design choice with various options that could be coherent, non-coherent, use more taps from the ACF, or even track the multipath components, like the multipath estimating delay locked loop. Now, all these tracking architectures update their estimates with a filtered version of the code phase error. So in essence, they are just functions that map taps from the ACF to the change or error in the code phase. Now, during normal operation, this function is approximately equal to the code phase error. However, when multipath is introduced into the system, it corrupts the ACF, distorting it and leading to multiple peaks, as we can see here with experimental data. This leads to errors in the estimates produced by these functions, which we will denote by E. Now, E is just another function that acts on the same input space X, but maps it to the errors incurred by the tracking algorithm due to multipath. So we are proposing this architecture that aims to use the function E to mitigate multipath, but since we don't know what it is, we turn to neural networks for function approximation. So let's consider an unknown target function f that maps x onto y, which we would like to approximate with another function h. Well, to do that, we have to first find the hypothesis space with optimal complexity. In this illustration, we can hypothesize that h should be some combination of scaling and rotation. And then we have to find the optimal parameters, in this case the amount of rotation and scaling that would make h a good approximation of f. But what does good even mean? Well, all we have to work with is the given data set. So first, good is measured using the cost function, which defines the in-sample error that the learning algorithm seeks to minimize. But this doesn't really capture what good means. A good approximation is one that could be generalized and make predictions outside of the dataset. This is captured by the out-of-sample error, and to properly define it, we have to assume that the given dataset is randomly sampled from an exterior set with an underlying probability distribution, so that we could start talking about the out-of-sample error as the expected value of the cost function. The problem here is that we don't know the underlying probability distribution. So to train a neural network, there are good practices that one can follow to ensure that the out-of-sample error is close to the in-sample error, such as input data preprocessing to transform the data into an invariant space, regularization techniques which limit the complexity of the hypothesis space without decreasing its dimensionality, and using k-fold cross-validation, a data partitioning method used to estimate the out-of-sample error and assess a network's generalization capabilities. But before we talk about pre-processing the data, I have to tell you how the data was generated. We chose to simulate the environment around Aldrich Park at UC Irvine with the following trajectory and a constant velocity of 2 meters per second, and then used MATLAB's ray tracing methods to compute the channel impulse response. The ACF was then generated as follows and tracked by the DLL to produce the input, which is the ACF at the current estimate with nx number of taps on both sides. So after all that, this is the raw input we end up with. You can't really tell a lot from that, so before feeding this data to the neural network, we make it more invariant to changes that should not affect the output, such as the carrier power. That's why we normalize the input data by the tap with maximum magnitude, and then we separate the inputs into the real and imaginary components, so that our final preprocessed data looks like this. As you can see, even visually, we can extract more information about multipath in the last figure than in the first one. And now that we have our input, we need to find the optimal hypothesis space. So for feed-forward neural networks, we used 5-fold cross-validation to estimate the out-of-sample error and found that wider architectures work better than deeper ones. We also search for the best regularization parameter, lambda, which is a parameter that penalizes the weights of the network, allowing us to explore subsets of the hypothesis space. Then we move to time delay neural networks, which could be thought of as an extension of the previous architecture with delays on the input layer. To illustrate, this is what the feed-forward neural network was seeing, and this is what the TDNN sees now. In this view, the presence of multipath is more apparent, and we can even tell that multipath entered the system at this point, and see the ACF as it oscillates between constructive and destructive interference. And now for the simulation results, here you can see the true simulated code phase, and then the code phase tracked by the DLL along with its errors, the code phase corrected by the feed-forward neural network, and finally, the time delay neural network, which outperformed the feed-forward neural network as expected. Experimental data was then collected while following the simulated trajectory and used to validate the performance of the TDNN. You can see the code phase error increasing linearly for both the DLL and the TDNN. This is due to the clock drift, which over a short period of time could be assumed constant and is estimated as the slope of the dashed line. After accounting for that, we can see that the TDNN follows the DLL closely in the no multipath regions and tries to correct it in the multipath region, resulting in a lower RMSE. But this approach isn't the latest and greatest, and that's because of its main limitation. It's important to note the dependence of generating the training data on the output of the DLL. This implies that the deployed approach must include both a DLL and a proposed neural network, such that the output of the DLL is fed into the reference sequence generator, while the output of the neural network is fed into the navigation filter to produce a more accurate navigation solution. We can't completely replace the DLL because that would change the input space that was presented to the neural network during training. This also means that the neural network is specific to the tracking algorithm used, as a different choice would affect the input space as well. So in reality, the neural network is acting as a filter that corrects the estimates produced by the DLL instead of producing estimates itself. So how can we present the same input space during training and deployment without a tracking algorithm? Well, the solution is turning to reinforcement learning, which is more suited for control problems since the neural network learns by interacting with an environment in which the decisions taken by the neural network are meant to affect its inputs. So let me introduce the main components needed to formulate the reinforcement learning problem. The two main components are the RL agent and the environment. In general, an environment has internal states. In our case, that would be the physical environment and the states of the receiver. The agent, on the other hand, is responsible for taking actions that in turn affect the next state of the environment. The agent decides on these actions using what is known as the policy, which is a function that takes in state observations from the environment and chooses the best action. However, the agent can't tell a good action from a bad one, so we introduce a critical component, which is the reward. Remember that the RL agent doesn't know anything about what goes on in the environment. In order to get the performance that we want, we have to craft the reward function to incentivize the agent to do exactly that. And last but not least, we introduce the brains of the RL agent, the learning algorithm, which is responsible for updating the policy in order to maximize the long-term reward. Now, in order to successfully train the agent, we had to make some important design choices. The first is the choice of a discrete action space, which limits the neural network to updating its estimate by either 0, alpha, or 2 alpha. This helps protect against singularities in the output, where a specific input could trigger very large errors. It also helps ease the learning problem for the agent because it has a lot less options to choose from. Note that the parameter alpha is analogous to the bandwidth of a first-order DLL, as it defines the maximum rate of change that the agent could successfully track. And now for the reward function, it was crafted to penalize the code phase error and its first-order derivative. We also added a milestone reward for surviving 5 seconds, where surviving means never exceeding a code phase error of the bandwidth of the signal over 4. When it does, the agent is killed and another episode is started. This helps with initial convergence as it filters out the agents that are immediately killed and gives the agent a push in the right direction. And of course, we have to design the neural network which will ultimately be deciding the action to be taken. For this approach, we implement a convolutional neural network with 16 21 by 3 filters that are shown here and had the following architecture with about 43,000 learnable parameters. Note that the input consisted of 21 ACF taps and 10 delay taps, and that the agent was trained using the same simulated environment around Aldrich Park. For testing, however, an experiment was conducted in Costa Mesa, California, where we listened to the two G-Node bees shown on this map along with their specifications. We can also see the starting point, which was 1.4 kilometers away from the first tower and 700 meters away from the second. And now you can see the GNSS IMU solution in green, along with the 5G solutions utilizing the DLL measurements in blue and the RL measurements in red. On the bottom left, we can see the code phase estimates produced by both algorithms. And if we look at the highlighted portion of the data between 20 and 30 seconds, we can see the ACF being corrupted by multipath, causing the DLL estimate to become biased, while the RL agent's estimate is not affected. Finally, the experiment results are summarized here, showing the RL agent reduced both the RMSE and maximum error by 31% and 20% respectively. I would like to thank these funding agencies for making this work possible, and I would also like to thank you for attending my presentation, and I'd be happy to answer any questions.